geometric invariant theory. And I've titled this reductive and non-reductive because I want to try to tell a story that goes from, arguably from the late 19th century, but let's say for the sake of argument, the 1960s up until the present day. So hopefully towards the end of this course, there'll be some stuff which is new to pretty much everybody. So the plan is to spend a lecture today sort of motivating the problem and setting it up. And then tomorrow will be Mumford's classical GIT for reductive groups. Then I'll talk a little bit about the structure of stability on Wednesday. And then Thursday and Friday we'll be talking about non-reductive GIT, which is a more sort of recent thing. So, okay. So to explain geometric invariant theory, I thought the best place to start would be the first page of Mumford's book, Geometric Invariant Theory. And so here you can see hopefully the preface to the first edition. And it says, the purpose of this book is to study two related problems. And one of them is about can we quotient algebraic schemes or algebraic varieties by actions of algebraic groups? And the second question here appears in this lecture course primarily by way of motivation. So hopefully you'd agree that quotienting algebraic varieties by group actions is going to be a thing we're going to want to do. It's an interesting question in its own right. But Mumford here says, perhaps rather provocatively, that the construction of moduli schemes or moduli spaces is just a special case of quotienting by group actions. So, this was said quite a while ago. So maybe we don't believe this is literally true anymore, but nevertheless, there's a very close connection between these two types of question. So let me try to explain a little bit what Mumford meant by saying that one of these things is a special case of the other. So the motivation here is that often we can write down a space, let me call it X, which, speaking rather loosely, I'll just call objects plus extra data. So these objects, whatever they might be, will depend on the moduli problem we're talking about, but they're going to be objects in algebra or geometry, algebraic geometry, that we want to classify up to some notion of equivalence. And often when we write down this set which parameterizes the space which parameterizes things with this extra data, the extra data is captured by a group action. So often it comes equipped with an action of some group G, such that the orbits under the group action are in one-to-one correspondence with equivalence classes. So again, what we mean by equivalence class is going to be something that we will be choosing depending on what type of thing we want to classify. So it's going to mean different things in different contexts. Okay, so let me give you a couple of examples. One of the nice standard examples that everybody has seen is endomorphisms of the vector space V. So let's say T, V to B. Okay, of dimension n. And the notion of equivalence here is fairly straightforward. You might want to say that that T is equivalent to T prime if they represent the same linear transformation up to choice of basis. So if there exists some automorphism of V such that, and then alpha T is T prime alpha inverse. So you can phrase this in terms of a particular square commuting if you want. And the point is that if you want to specify a linear map, the obvious way to do it is to write down a matrix. So our parameter space X here could be just n by n matrices. And this is an affine space of dimension n squared. And these things parameterize T plus choice of basis. So if we want to classify these endomorphisms up to equivalence, then what we really want is an orbit space for this group action. So hopefully this is something that's going to be very familiar, but trying to put a slightly new, maybe a new way of thinking about it for those who've not thought about moduli questions before. And then let me just give you one other example, which is hypersurfaces. So if I have a degree D, let me not call it X actually. Let me call it S. Why not? So if I've got a degree D homogeneous polynomial in variables of x naught up to xn, then I get a degree D hypersurface in projective space. And here, again, there's a natural parameter space to write down that parameterizes these things, which is just the projectivization of the vector space of degree D polynomials, dual. And so when would we say that two hypersurfaces are really the same hypersurface? Well, a good candidate for what the equivalence relation should be is that we might want to say that S is the same as S prime if there exists some automorphism of the ambient projective space that takes one to the other. So this is a kind of baby version, if you like, of moduli varieties. And if you know about such things as Hilbert schemes and Chow varieties and Quat schemes and stuff, then you've seen generalizations of this sort of thing. Okay, right. So hopefully I've managed to convince you that quotienting things by group actions is a thing that we're going to want to do. The next thing I have to convince you of is that it is not trivial. There is a lot of interesting theory, and there's a lot of stuff that can go wrong here. Okay, so the problem is that so the naive quotient, just the topological quotient x mod g need not be a scheme or a variety. So I should say maybe at this point that I'm going to use the word scheme a lot, but nothing I say is really going to depend on knowing what a scheme is. So if you don't like the word scheme every time I say scheme, you can just substitute the word variety, and you won't have any problems. Okay, so why is this naive quotient not always going to work? So another way of saying this is that if we're just interested in topological spaces, then this is sort of a non-question. You just have the quotient topology, and that's a perfectly good topological space, and there's nothing more to say. But in algebraic geometry, things are a lot more rigid. So it's a lot more difficult to get something that's actually a genuine algebraic object. So the standard example that people like to use to illustrate this is, if you think about GM, the multiplicative group of whatever field you're talking about, acting on affine 2 space via T on XY, being, let's say, Tx, T inverse Y, then, okay, so what do orbits for this action look like? Well, there's sort of 4 different kinds of orbits, really. There's things that look like xy equals alpha for alpha non-zero. There's punctured axes like this. So this is, axis minus the origin, and then you've got the other axis minus the origin, and then finally you have the origin itself. And these are all orbits. So if we took if we just took the topological quotient, then what would this look like? Well, it's sort of not too difficult to convince yourself that the quotient really ought to be the affine line. But if you just do the naive topological quotient, you get something quite funny. You get a sort of punctured affine line, which is coming from these. And then these 3 things are all sort of competing because they all want to be the origin of this affine line. So you actually have 3 origins, and this one is a closed orbit because it's just a point, and these 2 are not closed orbits. So in some sense, in the quotient, the closure of this thing should have this in it. So you've got non-closed points, which is sort of a bad situation. That's telling you maybe that something's not going so well when you have orbits that aren't closed. So another another problem that can occur is that sometimes what you'd like to do is, rather than quotienting the whole variety, sometimes there's an open subset of your variety that has a nicer quotient. So the standard example of this would be if you take GM acting on affine n space just by T x1 to xn, just scaling everything like this. Then if you think about an minus, if you think about an itself quotiented by the GM, then this is bad because all of the orbit closures are meeting at the origin. But if you remove the origin, then you get, of course, projective space. So the point of this example is to say to you, well, sometimes actually, maybe you don't want a quotient of the whole thing. Sometimes what you want to do is have some clever way of picking out an open set that has a nicer quotient. So if you've not encountered GIT before, then this is really the notion of semi-stability. That's sort of what that is meant to capture. And then one final thing to say is that so from both of these examples, you'd be forgiven for looking at them and saying, aha, I see what the problem is. The problem is that orbits aren't always closed. So if you just always have closed orbits, then everything is going to be fine. And that is a reasonable thing to think, but it is also not true. So there are examples where the orbits are all closed, but the quotient is still very bad and not the right answer in some sense. So I will not prove this, but there is an example due to Winkelmann of GA, that's the additive group, acting on A4, let's say over the complex numbers. And I'll tell you what the action is. It's not particularly important what the action is precisely, but I will tell you what it is. So this is, let me move this here so I have more space to say. So this is x plus u times z squared minus 2w minus 1, y plus uz plus u squared over 2 w, and then z goes to z plus uw, and w is fixed. So perhaps that's not very enlightening, but anyway, just for the sake of completeness, I've told you what it is. And the point is that all orbits are closed, but the topological quotient, let's say, well, yeah, the quotient, let's say, is not Hausdorff in the analytic topology that comes from the complex numbers. So there are other examples that exhibit this behavior, but anyway, here's one of them. So the point of this is to say, well, it is not simply enough to make sure that all the orbits are closed. There's more subtlety going on here than just that. So some fairly pathological things can happen. And so what's the sort of strategy of GIT? Well, usually we do.
Can you scroll up? Can you?
Can I scroll up?
Yes, thank you. Thank you.
Cool. Yeah, sorry, I move very quickly when I'm writing landscape. Right, so the strategy is in general to do a combination of two things. So one is to throw away bad orbits. And the other thing is to glue orbits together. So this is, for number one here, you should think about this example. So clearly the origin is kind of a troublemaker here. If we get rid of it, we get a lovely, a projective space of dimension n. If we leave it in, we get some horrible mess. So what we ought to do is get rid of the origin. So in other words, we're kind of weakening our notion of quotient in the sense that we're saying we're not going to get a quotient of everything. We're just going to get a quotient of an open set. And the second thing here is to say, well, we're going to weaken our notion of a quotient in a different way, which is to say we're going to abandon the idea of getting something which topologically is an orbit space. Sometimes that's just not going to be sensible. It's not going to be possible. So these are the two kind of tools that we have, and GIT is a systematic way of doing, in general, both of these things. Usually, we have to do both of these two things. So I've told you that we're not going to get something which is always going to be an orbit space. So we need to kind of come up with a new notion of what quotient means, you might say. So let me give you a definition. Okay. So so a map phi from x to y is a categorical quotient categorical quotient of some G action on X if it's G invariant, and for all G invariant maps, let's say psi, from X to some other thing Z, we can fill in the diagram in a unique way. So this is a sort of definition by universal property. So here's phi, here's psi, and then what I'm saying is that there exists a unique map here that makes this commute. So this is the universal property that makes something a categorical quotient. So you should think of this as like the best possible answer that we could get in whatever category we're working with. So you could consider categorical quotients in schemes, varieties, whatever sort of thing you want. But this is the sort of easy to write down definition of what's the best possible thing. And by the usual arguments, if it exists, then it's unique up to unique isomorphism. So this has that, which is the usual advantage of defining something by universal property, but it has the usual disadvantage of defining something by universal property, which is we have no way of knowing whether it exists. And even if it does, there's no reason it should be especially nice. Like the best possible answer could actually be quite bad. So what we're going to need is some kind of method of generating categorical quotients, sort of determining whether they exist. So let me introduce what I'll call the basic idea of GIT, which we have already seen in Ali Craw's talk. By the way, I should thank Ali Craw for stepping in at the last moment and saving me when we had our technical issues this morning. I think we were having some trouble with the diesel generator or something, so that was the problem. Sorry about that. Yes, so the basic idea of geometric invariant theory. And if you like, this is where the I comes from in GIT. So I'll tell you where the G comes from later, but this is where the I comes from. So if we let a linear algebraic group G act on, let's say X, which is spec A, an affine scheme, or if you prefer, an affine variety, either one is fine. So a linear algebraic group is a linear algebraic group is an affine group scheme. So I'm going to be working over an algebraically closed field of characteristic 0. So I don't have to worry about whether it's smooth or not. But you should just think of it as like a closed subvariety of n by n invertible matrices, if you like. That's a perfectly good way of thinking about it. Okay, so the basic idea is that whenever we have this sort of situation, well, we get an action of G on A so if we take some F in here, then if I want to evaluate this at a point, I can just define this to be F evaluated at the point G inverse P. So this is for G in G and P in X. And if you want to think about things in a more schemy way, if you like that sort of thing, you could equivalently think about it as a coaction, like this. So this would be called the coaction. But don't worry about this too much if you haven't seen it. It's just a sort of kind of, it's a way of seeing group actions on the ring side under the equivalence of categories between, say, affine schemes and K-algebras and so on. But this definition is going to be good enough for our purposes. Okay. So the point of this is that if we have an action on X, we get an action on its ring of regular functions. So we can define the invariants. There's a notion of invariant function because now I've given you a group action on the algebra. So this is F in A such that GF equals F, G in G. It's the obvious definition of invariance. And if you think about it, you can easily see that this is a subalgebra. Okay. And so this thing which I want to call the basic idea of GIT is that the way that we should get quotients is that locally they should be spec of invariance. So this AG has this inclusion here. So this induces a map of affine schemes, which I will call phi, which goes from X, which was spec A, remember, to spec of a G, which for now I will call Y. So if you've seen this before, then you know there's an equivalence of categories. So if I get a map in one direction for the rings, I get a map in the other direction for the schemes. And if you haven't, then you can sort of take my word for it that if you have a map of regular functions, you get a map of spaces in the opposite direction. So the basic idea is that we should affine locally. Our GIT quotient wants to be spec of invariance. And then if we want to do something which is not affine, we're just going to glue that together in an appropriate way. Similarly to what Ali Craw was saying. Okay, so I'm going to give a definition now, which is a way of sort of formalizing the idea of a quotient, which first of all is locally spec of invariance, and second of all, it doesn't glue things together too much. So let me tell you that definition. Okay. So this is going to be another type of quotient. So we've seen categorical quotients. This is going to be another type. So again, we've got G acting on X and phi from X to, let's call this thing W. Morphism schemes. Okay, so then we say that phi is a good quotient so three things. First of all, we want phi to be, so it needs to be G invariant. If it's going to be a quotient, it should be invariant under the group action. It's surjective. Hope you agree that quotients should be surjective. And we also want it to be an affine morphism. If you don't know what that means, then don't worry. It's just a technical thing that's not really going to play too much of a role in what I have to say. Okay, so the second thing here is that I need OW to be isomorphic to the push forward of OXG. So this is some condition on the structure sheaves of these things. But what this is really saying is that locally it looks like spec of invariance. So again, if this notation is unfamiliar to you, then I wouldn't worry about it. It just says locally it looks like spec of invariance. And then the third thing is to say that I don't want to be gluing orbits together unnecessarily. Oh, yeah, there we go. So I don't want to be gluing orbits together unnecessarily. So we've accepted that there's going to have to be some gluing together of orbits, but I don't want to be doing it just willy-nilly all over the place. So I'm going to have some definition which is going to say I've only done the minimal amount of gluing, and that's just what this is going to say. So this is if W1, W2 inside X are disjoint, closed, and invariant, then their images are disjoint and closed. Okay. So one thing to observe about this, if you have seen these sorts of things before, is that this definition is local on the target. So I can construct good quotients by locally gluing things together, which is good because I want to construct them by locally gluing together spec of invariance. So that's an important property that's going to come up. Okay. So this definition, just to repeat, is meant to it's meant to sort of formalize the following rough ideas. So so a couple of remarks about this. Oh yeah, the first thing to say is that good quotients are categorical. So if I have a good quotient, it is for free a categorical quotient, which means it is for free the best possible answer in an appropriate sense. So that's good. Okay. Yeah. So just to write down what I said in words before. So part 2 of the definition says locally it's spec of invariance. So let me say what that means in a little bit more detail. So if I have some open affine U, which is say spec B inside W, and phi inverse. So the fact that the map is affine will allow me to take pre-image of this and get something which is affine. So phi inverse of U is, let's say, spec of, I don't know, let me call it B prime. Then if I take phi up a star, then I'll have B goes to B prime G invariance inside B prime, and this map is an isomorphism. So the quotient map identifies, if you like, identifies locally the regular functions on the quotient with the invariant regular functions on the thing I wanted to quotient. Okay, so that's the first two, and then the third one. The third thing I want to say about this definition is this idea of minimal gluing. So yeah, so number 3 says minimal gluing. So one way to see this is if I have, let's say, two points in X, then they get sent to the same thing if and only if their orbit closures meet. So this is sometimes called S equivalence. The equivalence relation that your orbit closures meet in the locus being quotiented is sometimes called S equivalence. So you can see immediately that you're going to have to identify 2 points whose orbit closures meet. There's no way to not do that and get a reasonable space from our point of view. So this minimal gluing is saying, okay, well, you have to do that, but that's it. You're not doing any more than that in some sense. Okay, so in this situation, then topologically we have that the quotient is it's X modulo this relation of S equivalence, which is this. We say 2 things are equivalent if this is true. So in particular, if orbits are all closed, then we actually do get an orbit space. So that's sort of handy. It's saying in a nice situation when orbits are closed, we will get something which is what we'd most like to have. Okay, so and I may as well, while I'm here, give you the definition of what we call it when that happens. So if we have a good quotient and topologically it's just the quotient topology, we say that phi is a geometric quotient. So a geometric quotient is like the Holy Grail. That's the thing we'd most like to have. But there are various other things we might want from our quotients. For example, if we quotient something projective, we might want the answer to be projective. So there's going to be various trade-offs that we're going to have depending on whether we care more about getting a geometric quotient or whether we care more about getting a, say, projective quotient. Because maybe we really want to have a compact moduli space for some purpose, like maybe we want to do enumerative geometry or something like that. Okay, so this all seems quite good. And let's just sort of test this idea of spec of invariance for one of our examples. So the GM acting on A2, the example I gave before with this thing, Tx, T inverse Y, then what happens? Well, then the invariance is a xy, that's the product xy. So this is, of course, isomorphic to just a a polynomial ring in one variable. So A2 to A1 is the quotient from spec of invariance. So if you recall the picture that I drew here, we had these sort of nice closed orbits, and then we had these three origins that all wanted to be the origin. And what this has done, if we take spec of invariance, is it's glued those three things together. And it says, okay, fine, if you all want to be the origin, you can all be the origin. And then it just glues them together. Okay. So that seems very, very good. It's, it's given us more or less what we wanted. Clearly gluing those three orbits, those three origins together was sort of necessary, and it hasn't done any more than that, so that's quite good. So it seems like this spec of invariance thing is a good thing to do. However, it doesn't always work. Okay, so let me give you an example to show you why. So if you consider GA acting on SL2, so I'm thinking of SL2 here not so much as a group, but as an affine variety. And the action here is going to be via, so if I have alpha in GA, then I'm going to send this to this matrix, and that's going to act on the element A, B, C, D in SL2. So it's just left multiplication. Okay, so that seems reasonable. But then the problem is if I take the invariance, then what I get is I get a polynomial ring in two variables, C and D, and you can sort of convince yourself that these are the invariants. So what you get is you get a map from X to A2, but, and this is the crucial thing, the image of this map, the image is A2 minus the origin. Why is that? Well, you obviously can't have both C and D vanishing and the matrix be invertible. So if you're if you're mapping out of SL2, then one of them has to be non-zero. So you're not going to hit the origin. So why is this a problem? It's a problem because the map is not surjective. So it doesn't really deserve to be called a quotient if it's not surjective. And if you think about it, you can sort of convince yourself that if I have a map which is not surjective, then it couldn't be a categorical quotient because I ought to be able to sort of remove remove some of the points that aren't in the image and make it smaller, So that's bad. The spec of invariance does not always give you a surjective map. That's pretty bad. Okay. And then one other thing, which I won't give you an example of this, but this is just going to tell you that this is something that can happen. There exist actions, for example, of GA on A3, let's say, where invariants don't separate closed orbits. Closed orbit. And this is also bad, because that means we've glued things together that we shouldn't have had to glue together, in some sense. It's not going to satisfy this minimal gluing property if two, perfectly happy closed disjoint orbits are getting identified. That's not good. Right. So there's one other thing to say about this. So another problem, which has already been, I think, alluded to today, which is that computing invariance is hard. It's not something that we want to do if we can avoid it. I mean, there was a whole industry of Hilbert and people like that in the 19th century. Computing needs invariance, and this led up to the proof of Hilbert's basis theorem, the finite generation type proof. And in some sense, one of the reasons to compute the invariance and to go to that effort was because you weren't sure if it was going to be finite or not. Which sort of leads me on to the next thing, which is another important question, which is really at the heart of this subject, which is, so this is Hilbert's 14th problem, which was posed in, I think, 1900. Okay, and the question is A, G finitely generated if A is finitely generated? So this is slightly different from the formulation that Hilbert actually gave. I think he posed it in terms of polynomial rings and function fields, but essentially the question is, if I have, say, a finitely generated integral K algebra and I have a group action on it, then are the invariants always finitely generated? Well, we know the answer to this, and the answer was given by Nagata in, I believe, 1950. So it was a little while before we knew the answer to this, and the answer is no. So that's rather unfortunate, because if we like varieties or schemes of finite type, and we want to say quotient affine things by making the choice of, by saying it's spec of invariance, if we start with a variety, we'd like the answer to be a variety. And Nagata tells us this does not always happen. So that's yet another sort of complication at work here. Okay, so sort of partial sort of solution to this this problem of computing invariance being hard, which is to replace computation of invariance with representation theory. So that certainly doesn't solve all your problems, but it does make life easier. So I would argue that the part of the G in GIT is the idea that instead of just computing invariance all the time, you should be thinking about things in terms of representation theory, and that makes your life tons easier. So we will see that we'll see that tomorrow, I think. Okay. Are there any questions about what I've said so far? Okay, good. So far, I'm really just sort of setting up the problem and trying to set the stage. Okay, so if you've been watching carefully, then you probably have noticed that the examples where things have gone badly wrong have been GA, and that's not a coincidence. So the first step towards trying to find a decent theory of quotienting varieties by group actions is to say, well, it seems to be more difficult depending on what the group is. And going along with this, this last thing that I wrote, that we should be thinking about this in terms of representation theory, a very reasonable thing to do is to focus on those groups that have nice representation theory and try and see if we can bootstrap their nice representation theory towards them behaving well when it comes to taking quotients. And that's exactly what reductive GIT is about. So that's what I'm going to be talking about tomorrow. I'm going to get into all the details of reductive geometric invariant theory. But just to conclude today, I want to give you a little bit of structure theory of linear algebraic groups, because sometimes people don't know what a reductive group is, and I think it's very handy to have seen this. So let me just finish with that for today. Right. So here is some structure theory of linear algebraic groups. Right, so it is going to be important now and from now on that I'm working over a field which is algebraically closed and whose characteristic is 0. That is not to say that nothing that I will say from now on will work in positive characteristic. A lot of it does. It's just slightly more complicated, and I want to try to make things as simple as possible. And the characteristic 0 case is really a lot simpler. So I'm going to focus on characteristic 0, which is more or less how the subject started anyway. And the algebraic closure is just, you know, I just need that. Okay, so so I said this in words before, but let me just tell you. Let me just write it down. So what is a linear algebraic group? A linear algebraic group is an affine group scheme. Okay. A group scheme is, if you like, a group object in the category of schemes. If you don't want to think about it like that, you can just think of it as being an affine variety with a nice group structure, which is sort of where all the relevant morphisms that you want to write down are actually algebraic morphisms, like multiplication and so on. Okay, so that's the basic type of group that we're going to be talking about. And then I need to tell you what a reductive group is. Let me do that. So this theory of GIT really splits into two parts. There's reductive and non-reductive, and reductive is, very well understood in the 1960s. Non-reductive is an ongoing thing, which I personally spend a lot of time thinking about. So those are the two halves of the subject, and they're really quite different. So it's reductive if every representation, let me say every finite dimensional representation, just to be really pedantic, is completely reducible. I.e., there exists a decomposition of that representation into these things with each VI irreducible. So it has no proper subrepresentations. So this is what I mean when I say we want to first try to do GIT for groups that have nice representation theory. So this is what I mean by has nice representation theory. So the first thing you're going to ask me is which groups are reductive. So, well, finite groups, GLN, SLN, GM, products of these. So lots and lots of groups are reductive. It's it's a very common property. Okay, and let me tell you the fundamental non-example, which you can probably already guess, is GA. So, e.g., if I take GA acting on A2 by this action I already wrote down, this embedding into GL2, then 1, 0 is invariant. Sorry, the span of 1, 0, I should say, but not a summand. So, the one-dimensional linear algebraic groups, you've got GA and you've got GM, and GM is the nice, well-behaved one, and GA is like its evil twin. Things go wrong for GA just all over the place. And that dichotomy between GA and GM is, in some sense, represents it's the first instantiation of this kind of structure theory for linear algebraic groups. So let me give you the definition of sort of the opposite of reductive. So a linear algebraic group is called unipotent if it's isomorphic to a closed subgroup of upper triangular matrices with ones on the diagonal. So 1, 1, 0's here, and then whatever you like up here, this set inside GLN. So there are various different definitions of unipotent that you can give, but this is sort of the easiest one. It's the most hands-on. Okay, so when I say that these two things, reductive and unipotent, are opposite and sort of complementary, there's a way of making that precise. Okay, so every linear algebraic group, H. Oh yeah, so one thing is that I will try as far as possible in these lectures to use G for reductive groups and H for general linear algebraic groups, which are potentially not necessarily reductive, just to keep things straight. If I at any point don't do that, then someone shouts at me, because I want to keep that as a convention, because I find that to be helpful. So every linear algebraic group, H, has a decomposition into basically a unipotent thing and a reductive thing. So H, you can express it as a semi-direct product like this, with U, what's called its unipotent radical, i.e. it's the maximal connected normal unipotent subgroup, and R is a reductive group. So U is unique. So U is unipotent radical is a unique thing inside a linear algebraic group, and it measures how far away the group is from being reductive. So you could say, if you like, that a group is reductive if and only if its unipotent radical is trivial. That's also a perfectly good definition. Or equivalently, if and only if it has no connected normal unipotent subgroup. So there could be GAs hiding inside your group, just like there's a GA inside, GL2 here, but it's not allowed to be normal. Otherwise, the group's not reductive. So this thing here, this R, this is only determined up to conjugacy. So this is not sitting inside H in a canonical way. It's only determined up to conjugacy. And it's often people call this a Levy subgroup. You may hear that terminology. Okay. So let me give you an example, which is something that will come up later in our applications. So so if we have, let's say we have a filtration of a vector space. So let's say looks like this. So then we can define P inside GLN to be the parabolic group preserving this filtration. So it's just the elements in GLN that fix this filtration, right? That fix every stage in the filtration. So if you choose a basis in the right way, first choose a basis for V1 and then extend to a basis of V2 and so on, then if you think about what P will look like in that basis, it's going to be block upper triangular. So let me try to give you a sort of picture of that. So it's going to look something like this. Right, so P, there's going to be zeros down here. So P is going to look sort of like this. Right? So how can we see this decomposition for such P? So it's quite a nice way of expressing it now that we've got this this basis here. So the unipotent radical of P is the set of things which are in P, so they're block upper triangular, but I have to have identity matrices on the diagonal. So all of these diagonal things have to be the identity. And there'll be identity matrices of different sizes, depending on what the dimensions of the steps in the filtration are. But and then of course you're allowed to have whatever you want up here, anything up here. Okay, so that's U. So let me write down what a Levy R would be. And this thing is where I take the things on the diagonal and then I put 0 everywhere else. So here, let's see, color these in red. Here, red is 0 and blue is anything. So that's for R. So you can see if you think about it, what is this going to look like? Well, it's going to look like a product of general linear groups of different sizes, because I need each of these elements to be invertible in order for the whole thing to be invertible. So R is going to be a product of general linear groups and therefore reductive, because I told you that GL GLM is reductive and products are reductive if everything in the factors is reductive. So hopefully you believe me that this is reductive, and this is certainly unipotent because I gave you the definition and I've said, well, it's just ones on the diagonal, so I've got identity matrices here. And if you think about it, you can convince yourself that you can express P as a semi-direct product like that. Okay. I think that's everything that I wanted to say for today. And so tomorrow I'm going to talk about Mumford's reductive GIT. Thanks.
Are there any questions from Josh here in Cambridge?
So the blue blocks up there, I didn't quite get if those are identities, well, I guess not.
In the R case?
The P.
Oh, in the P case, they can be anything.
It could be anything, right?
Right, it's still invertible.
So I didn't hear the question there. Was there a question?
There was a question, but it was just about the picture, so I answered it.
Okay, great. I think we may have to.
Yeah,
oh, okay.
Maybe you have to shout at the same volume as I am. Is that right, roughly, Josh? Can you hear me okay?
Yeah, or maybe if you just repeat the question, Vicky, that's
Sure,
probably
yeah.
fine.
My question is maybe for our field, I don't know, but I'm curious about GIT. You mentioned you're working over an algebraically closed field of characteristics 0, and you said something about maybe other characteristics. Do people ever do GIT over the integers?
Yes, you can. Yes. So if you look in Mumford's book, he does things like construct moduli spaces in this sort of arithmetic way. So either over spec Z or over spec Z where you've inverted 6 or that kind of thing. So yes, you can do that.
Okay, thank you.
Are there any other questions here? Then I think I pass over to Praise or Josh to ask if there are questions in Ividan.
Yes, I think we do have questions here.
Okay.
So question that so the half frame was not weighted out. Otherwise,
Yeah, so I'll just repeat the question for the benefit of the people in Cambridge. So the question was about it was related to this question of positive characteristics. So Praise said that there's a notion of linearly reductive, geometrically reductive, and reductive, and sort of what are these concepts and how do they fit together? And this is exactly the thing I was hoping to avoid by not talking about positive characteristic. So the point is that you have these different concepts which in characteristic 0 over an algebraically closed field, they all coincide, so you don't have to worry about the difference. Whereas if you're talking about positive characteristic, then there are some strict implications between them. So I believe 2 of them are still the same, and you have one direction of the implication, but not the other. So I guess the brief point of this is that if you're in characteristic P, you can still make everything work, but you just have to be a little bit more careful about what you mean by reductive. And a couple of the proofs are slightly more annoying to do as well. But yeah, I'm not going to be getting into that. One other thing that might be worth saying, if people are more differentially minded, then you can also think of reductive groups as taking a compact Lie group and taking its complexification. So that's another characterization of reductive groups, which is a bit more related to things like symplectic geometry, which I'll briefly touch on in future lectures. Have any other questions in the room here in Ibadan? No? No, okay, I think that's all the questions.
Okay, well then we'll thank Josh again and see you tomorrow.